Okay, so hi everyone, Senan this side, and today we are going to solve this LeetCode daily question, which is LeetCode 386, which is lexicographical numbers. Given an integer n, return all the numbers in the range 1 to n, sorted in lexicographical order. So this is the constraint that constants you need to use constant space and linear time. Now this assume this space is not including the vector that you're actually going to return. So it is not considering that space, because technically you would use a vector of size n, right, to return the answer. So we are just taking into consideration that space which is actually required into solving the problem. Now the input is quite straightforward. When n is 13, so 1, then 10, then 11, 12, 13, then 2, everything that starts with first, everything that starts with 1, then 2, 3, 4, 5, 6, 7, 8, 9, similarly like that. Now after, in this case, you see 0, 0, 1, 2, and 3. So this is the classic lexicographical order. I'll show you two solutions. Both of them work, but only one of them is actually satisfying this concept, big of n and big of 1 extra. Now for n is equal to 2, 1 and 2. So this is the constraint. Now when you see this constraint of n, you could actually see that you could actually easily be able to do an n log n solution, right? Because n is somewhere of the order 10 to the power 4. And I don't know if you could actually do it with n square using some sort of bubble sort algorithm, but anyways, look at one of the solutions, then we'll look at the one of the solution that does not satisfy this, and then we'll actually see in the notebook how do you solve with this constraint. So the idea is simple. In the first solution, you create a size n vector and you fill all the elements in this vector from 1 to n, and in the end you return this answer. But what you do in between is what is actually important. Now you actually sort this answer list, and I have taken a lambda function. What it does is takes an integer a and b, converts them to string, and then does the lexicographical comparison. So when you compare strings, it's a lexicographical comparison. So that is what I'm trying to do, converting every integer into a string, and then just using this overloaded symbol greater than operator is or less than operator, you could actually do the comparison. Okay, so since you know that the size of the element is 5 times 10 to the power 4, that means it can have at max 5 characters. So this comparison would be big of 5, right? This is a constant time comparison given the length of the string. But if you technically see, the length of the string could be any finite number, so that would actually cause some issues if you are not knowing what is the upper bound of this n. So that's fine. Now let's look at the other solution, which actually before that, this is big of n space. Assuming we don't consider this big of n space, even after that, sorting, if you're using merge sort, it takes big of n space for sorting. So anyways, you're using big of n space and n log n time. But this works. I've tried it. It was accepted. So this works. Now the next thing is the second way, and I think that is the actual way that you have to do this. And now let's look at my notebook. So here we are, and this is a tree, and more or less this is the lexicographical tree of integers. So first, if you see all the numbers, first you will have 1, and before you can have 2, you need to have all the numbers start from 1. Now you have a 10, and then you have 100, right? Then you can go towards the right or the next sibling to find the next lexicographical number. So in a way, this tree is representing all the lexicographical sequence that you need to know. So 1, then you have to go to 10, then you have to go to 100, then 101, 102, till 109, if there are no more branches below this, right? So for example, let's take n as 102. Why 102? Why not? So that is the idea. So let's take n as 102 and let's try to fill the 102 elements in this list. Obviously I won't do it for every number, but we'll see one by one and how do we actually do this. So first I'll take a value equal to 1. I'll start with this, right? And just for safety, I'll just write it properly. So val is equal to 1. So now what I do is I go here and I see this 1. And what I do, since my n is 102, I'll take this value, right? 1. Now before going towards the right to the next child, I need to travel down. So basically a depth first search. Given this tree, you have to perform a depth first search. Now you go to one step down. So again, this 10 that you see is less than 102, right? So you can take this value as well. After that you take 10. Now given this 10, you can again go down, right? Because 100 is still less than 102, so you take this value 102. But now when you try to go one step down, which would be what, 1000, this value is actually greater than n, right? So you cannot have this number in your list, because this list can only contain numbers n belonging to set 1 to 102. So any number outside this range cannot be a part of this list. So this, since we are reaching a number 1000, we don't take this value. Let me just remove this. Sorry, this is not 102, this is 100, because we reached here, right? So now we cannot go one step down. So what I do is go to the next sibling, which is 101. Now 101 is less than 102, so I'll take that as my, okay. Now I reach here. What I do is I take the next child, next sibling, which is 102. So I'll take 102 and I'll try to go one step to the right. And whenever we are traversing to 101, we also check the children of that node. But since any number multiplied by 10 when you go down, so it is at least 10 times this number, so you cannot actually do that, because that value would be greater than n. Okay, so you reach 102, that you have taken as a part of your answer. Then you try to go to 103. When we are traversing, this is currently 102. So from the start, if you see, when we reached here, this was 1. When we reached here, this was 10. When we reached here, this was 100. When we tried to go down, we could not actually get this, so then we went to 101 here. Then we made this 102. Now we're trying to go to 103. Now whenever I tried 103, this goes beyond this, so that means we have completed all the elements in this level of this branch. What I do is I go back. So from, I had 102, right? So 102. Now I go the next branch, so this would now be 11. So the next I would take 11, and clearly if you multiply this by 10, then you would get 110, and that number is actually greater than this, so you don't go down anymore in this branch. So what you do, you take 11, 12, 13, 14, 15, dot dot dot, till you reach 19. And when you reach 20, so 20 is not a part of this, right? So what you do, you backtrack in a way. You go to the next branch, which is 2, and in 2 you'll get 20. After this you'll get 2, then 20, and so on. So this is the idea. Basically what you have to do is to understand this tree, and how are you going to manipulate. So let's say we had not 102 but 110. Let's say you had 110, so you would have reached till 109, and when you go to 110, you see you have to change the branch, right? You go to this one. Now for example, you had a number like 2000, right? So you have 1999, right? This would be 2000. The next number would be 2000. So you don't go to 2000. So let's say somewhere down the line you have 1999, and next number is 2000, and let's say n is greater than 2000 the moment. So now when you try to go to 2000, so this is not a valid sequence, right? You cannot, from this you cannot actually go to 2000. You have to go to 2. So what you do is you divide this number by 10 repeatedly till the time you reach a number which is actually valid. So I'll divide this 2000 by 10 to reach 200, divide by 10 to reach 20, divide by 10 to reach 2, and through this I can actually continue the process of taking input. So this was the idea. Actually perform a depth first search in this tree. If you don't understand how we are going to do this, I'll show you the code. But before that, the thought that you would be thinking, that if you write a recursive depth first search, right? So recursive depth first search would use the recursion stack space. So that is actually a space that's not then big of fun. Then how would you do? Or if you construct this depth first search tree, for some reason, again, that won't be constant. So how are you going to traverse the tree with big of one space, because you cannot create a tree, right? Nor you're given a tree. So we have to find a way to travel this tree without actually having this tree. And this is where these numbers come into play, this numbers and this n, which allows us to hypothetically have a tree and traverse that tree. So now let's look at the code, and that will help you understand this better. So here we are back in the code editor. So clearly I initialized val as 1 and declared an answer length n, and what I do in the end, I return that answer. Now for every element that I have to fill in this list, I'm iterating through every location and I am finding a correct value for that. So val is initially 1, so answer of I is equal to val, right? Now what I do is I see if val start 10 is greater than n. So this is actually meaning that we are at the bottommost branch or the bottommost level that we can actually be in. If you remember that when we reached 100 in the test case or dry run. Okay, so now if that is not the case, let's look at the else one. So if I is right, so this value is 1, and let's say n is 102 again. So I have to go to 10, then 100, then 1000, until the time I don't actually invalidate a location. So val star 10 is less than n, so we are still within the domain. So what I do is I multiply this by 10, right? So from 1 I go to 10, I go to 100. From 2 I go to 20, I go to 200. 3 I go 30, I go to 300, like this. And that is how I'm going down in the tree. Now let's say val star 10 is greater than. So what do you do in that case, right? So you're at the bottommost level that you can actually be in. So you do a couple of things. Val is equal to n, right? So you are at the last number. For 102, in the case we had 102, this val is 102. For this test case, n is equal to 13, this val is equal to. So when I see val equal to n, that means I'm done level. Even though if that level has more elements, I don't need to search those elements. They can never be in my solution. So what I do is I in a way backtrack one step. I go one step up. Now when I go to one step up, so from 102 I'll go to 10. So 102 by what? 10 is 10, right? Because it's truncating out the decimal numbers. So after that I increase that value, right? I go to the next, that val plus plus is just going to the next position. So if this if statement is true, if I reach from 102 I reach 10, I go to now 11, and if I am val is equal to 100, I can go till 102. So this if statement is never executed. So from 100 I'm going to 101, then 102, like that. Now this is the case of the example where I showed you from 2000 we go to 200 to 20, then to 2. So this is this. So if you reach a number which is ending in 0, that means you now have to change the branch. You have to backtrack. You're the last element of that branch. So while val modulo 10 is 0, that means the number has zeros in the end. You just backtrack to the top, right? So from 1999, when you reach 2000, you go to 200, you go to 20, you go to 2, you go to, okay, you stay at 2, don't go before. And that is actually the solution. So if you do a dry run, this would actually traverse the whole tree, or the first n elements of the tree. So this is the idea, this is the way this is actually taking big O of n time. Why? Because you're traversing for all the elements, right? From 1 to n, right? And you would say, no, it's not exactly, this is not exactly big O of n because you're using a while loop, right? So but I would go against that, because you have a maximum number of 5 into 10 to the power 4. So at max, this while loop would run not more than 4 times. At max you would have this while loop running 4, and that's as good as constant time. So you could actually write 4 if statement inside this, and that would still work fine because given the constraints. So if you see, this is constant time operation. All of this is constant time operation, and you're doing this constant time operation for n times. So that is big O of n time. And although we are using big O of n space, and this question is not assuming that we are using this question is not taking this as an extra space, but depends how you interpret this space complexity. Regardless of that, in the end you return the answer. So basically you call the copy constructor of this on this answer, and that would create a copy of this n sized vector. That is what is going to be returned the caller. So yeah, that was the whole video. Hope I was able to explain this to you. Hope the diagram was clear. Anyways, thank you for watching this video, and I'll see you in the next one.